So, then we can look at another generalization of the problem, and the second case of the generalized isoperimetric problem is when we have multiple isoperimetric constraints. Multiple isoperimetric constraints. So, then what to do in this case? So, we see that suppose again let us set up the problem. So, suppose I have y being the extremal, y is the extremal of j of y. So, y being the extremal of j of y subject to I 1 of y is equal to L 1 and I 2 of y is equal to L 2. So, we have two isoperimetric constraints, right. To meet both constraints, okay. So, now how to derive the condition or the necessary condition for y. So, that y should satisfy. Now, again let us go back to our discussion on the standard derivation of Euler-Lagrange. We were perturbing in a standard derivation of Euler-Lagrange, we were trying to find the first variation delta j of y, and then we looked at subject to one constraint, that is I of y is equal to L. Now, given the fact that we have two constraints, we cannot perturb freely. We have to perturb in such a way, we have to perturb our extremal in such a way, so that the extremals always satisfy both the constraints simultaneously, right. So, what I just said is the following: to meet both constraints, and have an arbitrary term to meet both constraints and have an arbitrary term in variation of y, we use the correction terms. We use the correction of y, we use the correction term, right, y hat, which is equal to the perturbation of y as follows. So, epsilon 1 eta 1, epsilon 2 eta 2 plus epsilon 3 eta 3, right. So, this is my regular perturbation, and these quantities are such that these satisfies I 1 and I 2. So, these quantities are introduced so that I 1 and I 2 are satisfied. The two isoperimetric constraints are satisfied. Okay. So, then again let me introduce everything in the vector notation. So, introduce my epsilon vector, which is epsilon 1, epsilon 2, epsilon 3, and my eta vector, the perturbation vector, which is eta 1, eta 2, eta 3, and I see that eta k, my eta k are all second order differentiable from x 0 to x 1, such that my eta k of x naught is equal to eta k of x 1 is equal to 0, right. So, the perturbations are such that they vanish on the boundary, that is needed for all sets of perturbation. So, again approaching in a similar way that we approached earlier for Lagrange for isoperimetric constraints, with one constraint we set up the condition for extremal as follows. So, the condition for extremal this time would be the gradient of theta of epsilon bar minus summation lambda k of gamma k of epsilon bar set equal to 0, right, where my gradient is the gradient operator is the following operator. These are the respective derivatives with respect to epsilon 1, epsilon 2, epsilon 3, and these are eventually evaluated at epsilon equal to 0. Okay. So, what I have is the following, and then finally, what we have is, so where my this theta functional, my theta functional is the perturbation functional. Okay. So, I am just rewriting the extension case. So, the theta functional is the perturbation function x 0 to x 1 f of x comma y plus epsilon eta comma y prime plus epsilon eta prime, right, dx, and my gamma k of epsilon is my isoperimetric perturbation in my isoperimetric constraints, which is, so this is the kth component, which is gk. So, my k is 1 and 2. So, k depends on the number of constraints that we have. Here we have 2 constraints. So, gk of x comma y plus, so this is the perturbation here is y plus inner product of epsilon bar comma eta bar here, right. So, that is how the dot product. So, y plus epsilon eta comma y prime plus epsilon eta prime, right, dx. Okay. So, these are my following functions. So, let us say this expression is 1. So, this condition is 1, and again following the derivation that we did for the single isoperimetric condition, we see that 1 eventually reduces to the following condition x 0 to x 1 eta j of del f del y minus the regular derivative with respect to x of partial f partial y prime set equal to 0, with f now equal to small f minus lambda 1 g 1 plus lambda 2 g 2, right. Okay. Notice that the term epsilon 1 eta 1 is arbitrary. So, we just want to remark that the term epsilon 1 eta 1 is arbitrary with corrections epsilon 2 eta 2 and epsilon 3 eta 3. The corrections are due to the respective isoperimetric constraints. Okay. So, which means this condition can now be reduced if we use lemma 2 in our lecture 2, we can reduce this integral constraint into the differential constraint with the following condition. Okay, where f is this following, and let me call this condition as my condition 2, which is the necessary condition for the extremal. Okay. So, then that concludes the derivation of the necessary condition, except we need to remark a little bit about the existence of the Lagrange multiplier lambda 1 and lambda 2, whether under what conditions what are the conditions under which these constants lambda 1 and lambda 2 exists. So, what we are trying to discuss is the condition we are discussing is the condition for the existence. So, whatever we derived so far, whether it really makes sense or not, or in other words, does this lambda 1 constants lambda 1 lambda 2 at all really exists or not, okay, such that this condition 2 produces an extremal. Okay. So, well, again, so what is the condition? Let us recall the case for single isoperimetric constraint problem. All we did was we checked the rank of the Jacobian matrix and the rank of the augmented matrix, and it turned out that the rank in that case, in the isoperimetric problem with single constraint, the rank of the augmented matrix has an upper bound which is the rank of the Jacobian matrix, and similarly it is the same situation in this case as well. So, we consider the following. We consider this Jacobian matrix at 0, which is epsilon 1 equal to epsilon 2 equal to epsilon 3 equal to 0, all the epsilons set equal to 0, and what we have is, this is a matrix which is gradient of gamma 1 at 0, okay, and gradient of gamma 2. So, we have two conditions so far. So, we see that this is a this has 2 rows and this will have 3 columns, because there are 3 components epsilon 1, 2 and 3. Okay. So, this is of the form alpha 1 1, alpha 1 2, alpha 1 3, alpha 2 1, alpha 2 2, alpha 2 3, right, where my alpha I j is of this form, is integral from x 0 to x 1 eta j of del g I del y minus d d x of del g I del y prime of dx. Okay. And my augmented matrix will be an additional row, with the additional row replaced with the gradient of theta. Okay. So, my augmented matrix M f of 0 is the matrix M of 0 times grad of theta of 0, which is also equal to will be, the first 2 rows are similar, alpha 1 1, alpha 1 2, alpha 1 3, alpha 2 1, alpha 2 2, alpha 2 3, the same set of functions, and finally the last row will be beta 3 1, beta 3 2, beta 3 3, where my beta I j are, well the first, let index is always 3 here. So, beta 3 j are the gradient of theta with respect to epsilon, and set epsilon equal to 0, I get that x 0 to x 1 of eta j of this quantity del f del y minus d dx of del f del y prime, okay, dx. Okay. So, the condition for the existence, finally we are ready now to state the condition. The condition for existence of lambda 1 and lambda 2 is that the rank of the augmented matrix must be less than or equal to the rank of the Jacobian matrix. Okay. When that happens, we are guaranteed the existence of Lagrange multiplier leading to the extremal y. Okay. So, let us look at, we are going to end the discussion on this topic by looking at few examples. The example that I have in mind in this case is, we need to extremize again j of y, which is integral from 0 to 1 y prime square dx, subject to the constraint. We have two constraint I 1 of y is equal to 0 to 1 y dx, which is, and I 2 of y is integral 0 to 1 x y dx, and I set I 1, the first constraint, equal to 2 some value, and the second constraint is equal to half. So, and further we also have a set of fixed boundary conditions. We have two boundary conditions, y of 0 set equal to y of 1, which is equal to 0. Okay. So, we need to extremize j subject to the two constraints I 1 and I 2. So, the solution is, we directly look at the Euler-Lagrange equation here. So, we have our extended function f to be f minus lambda 1 g 1 minus lambda 2 g 2, which is which is the following function y prime square. Well, my f is the following quantity and my g1 is this quantity and my g2 is this quantity here. So, I have that this function reduces to this one times y minus lambda 2 times x y. Okay. So, then if I use my Euler Lagrange equation, I get, I am going to directly write down the ODE that we get. The ODE that we get is the following set of equation: 2 y double prime plus lambda 1 plus lambda 2 x is equal to 0, right. So, this is the equation that we get, and we can readily solve this equation, that is integrate this equation twice to get that y of x is minus lambda 2 of x cube by 6 minus lambda 1 by x square by 4 plus c 1 x plus c 0. So, we have 4 constants lambda 1, lambda 2, c 1 and c 0. However, note that we have 2 boundary conditions given by y 0 equal to y at 1 is equal to 0, and we have 2 constraints. I1 is 2 and the second constant I2 is half. So, from these 4 conditions I can readily find these 4 constants of integration and as well as the Lagrange constants. Students can directly check that we get the answer as follows. We get C1 equal to this and C2 is 0, well C naught. Okay. So, that completes the solution to this problem with where extremal is given by this underlined equation. And before we end the discussion on this example, let us also briefly look at the existence. Well, we already shown that lambda 1, lambda 2 are these values, but whether these values are unique or not, or we could possibly get another extremal for a different value of lambda 1, lambda 2, we just do not know unless and until we check the rank of the Jacobian and the augmented matrix. So, let us look at those quantities. So, for an arbitrary perturbation, we see that my alpha 1 j is the following integral. So, I have directly used, notice I have directly used these following formulas in our previous slide, where my alpha j's are these quantities. So, I directly plug in the integrand of the constraints to get alpha I j. So, my alpha 1 j is integral of eta j dx and my alpha 2 j is integral of x times eta j dx, right. And finally, my beta 3 j is integral from 0 to 1 to y prime eta j dx. Okay. So, notice, well, we do not know these perturbations eta j, but notice the following, that beta of 3 comma j is, well, it is integral of 2 y prime eta j dx, but this is also equal to minus lambda 1 times eta j dx minus lambda 2 times integral of x times eta j dx. This is directly from our Euler Lagrange equation. Well, what I am saying is this is directly from this particular equation that we are looking at this relation. So, which means that beta 3 comma j is negative lambda 1 of alpha 1 comma j negative lambda 2 times alpha 2 comma j, which means that my third row is linearly dependent, or the rank of, the conclusion is obvious here, that the rank of my augmented matrix is bounded above by the rank of my Jacobian matrix. Okay. So, that concludes the discussion on this example, and then let us now finally look at a third case of the generalization of the isoperimetric problem, that is the case of several dependent variables. Several dependent variables. Okay. So, we are talking about functional of the form j q bar, where q bar is a vector from t0 to t1 of L of t comma vector q comma vector q dot dt, subject to the isoperimetric constraint of the form I of q bar, which is integral of t0 to t1 of g of t comma q bar dot dt. Okay. So, we just look at the case with one isoperimetric constraint. So, we have that L and G are smooth, they have derivatives up to continuous derivatives up to second order, and let us say that q bar is a smooth extremal. Q bar is a smooth extremal of this setup, right. So, extremal for j subject to I. Q bar is an extremal of j subject to I with my boundary condition, q bar of t0 is q bar of 0 and q bar of t1 is q bar of 1. So, we have sets of vector set of two boundary conditions, two boundary conditions, each of them are vector conditions. Okay. And with my isoperimetric constraint of the form that I of q bar is equal to some constant L. Okay. So, the result I am going to directly state the result, because the proof follows the similar case for the problem with one variable, that q bar is an extremal, it is an extremal such that there exists a constant lambda, so that q bar satisfies the equation, the Euler-Lagrange, the system of Euler-Lagrange equation satisfies n Euler-Lagrange equation. Okay. It satisfies n Euler-Lagrange equation of the form d dt of del f del q j minus, well, let me just rewrite this equation in the next page. I see that my set of Euler-Lagrange equation are as follows: d dt of partial q k minus partial q k, this is q k dot of f, where my this is set equal to 0, where my k is from 1 to n. So, I have n constraints and my function f is L minus lambda g, right. My function is as follows. So, that is my result. Let us quickly look at an example to this problem. So, the problem I have is, I am going to revisit my DDoS problem. So, the DDoS problem now is set up with an isoperimetric constraint. So, this time we are going to determine a curve gamma of length L. Let me take L greater than 2, so that I remove the case of rigid extremals containing the points p minus 1, which is minus 1 comma 0, and the points p1, which is 1 comma 0, such that gamma is closed and the line segment from p1 to, well, so gamma is closed. We do not say anything beyond that, and 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 the area enclosed is maximum. So, essentially what we have done is, in the earlier version of DDoS problem, we were trying to stipulate the condition that a part of the curve lies on the x axis, right. So, now we have lifted that condition. So, we have lifted the restriction that gamma part of gamma lies on the x axis here. Okay. Well, certainly it passes through -1, 0 and 1, 0, but now the other half can very well be below the y axis. So, which means that we can have we have a much more generalized problem in this case. So, in this case now the area functional is going to be described by my Green's theorem, because this is a much more general scenario. So, my Green's theorem says that my area functional is given by j of q bar is nothing but it is equal to half integral of x y dot minus y x dot of dx. This can, well, my parameter is t and the dot denotes the derivative with respect to t. This can be readily found from any standard multivariate calculus text. And now I have the isoperimetric constraints. Isoperimetric constraint as follows. I see that I of q bar is also equal to integral from t0 to t1 square root of x dot square plus y dot square of dt is equal to L. So, this is my condition set equal to a constant L. So, now I have a case of constraint optimization with two dependent variables, and we directly set the system of two Euler-Lagrange equations, which are the following set of equations. So, let me directly write these two equations. d dt of, I am going to directly plug in the result, okay, minus y dot, this is set equal to 0, and then the second equation, let me call this as 1, and the second one is d dt of minus y dot divided by square root of x square plus y dot square plus half x dot is equal to 0. So, from here I can directly integrate the first equation to see that this gives me lambda x dot by square root of x dot square plus y dot square minus y is equal to c naught, and from the second I get that this is also equal to minus lambda of y dot divided by square root of x dot square plus y dot square plus x, this is also equal to c1, right. From here I see that, well, I can directly square and add from these two. I can directly square and add to see that my extremal will follow this particular curve. So, x minus c1 square plus y minus c naught square is equal to a constant lambda square. So, x and y are such that they lie on a circle with radius lambda, okay. And we have this equation has three unknowns c1, c naught and lambda, but we also have two boundary conditions. Plus we have one isoperimetric constraint, and that will fully determine the system, okay. That is going to determine my system or my unknowns C1, C2 and lambda, the Lagrange multiplier. So, I end my lecture, I end my discussion at this point, and in the next lecture I am going to talk about the situation where we deal with constraints of the form which are algebraic or holonomic constraints as well as non-algebraic or differential or non-holonomic constraints. So, thank you for listening. Thank you very much.